Newton's laws of motion, which is what we're dealing with in Year 10 science. So we're going to have a little look at what this PowerPoint's got to say. And the three laws are just summarised here. The first one's the law of inertia. The second one is force equals mass times acceleration, and the action-reaction law. So Newton came up with these laws. It was following on from the work of guys like Galileo, and has further been taken on from Newton. But his three laws have stood up to testing over decades of scientific research and testing, and haven't been seen to be contradicted. We see with them more or less it's a matter of them being incomplete, as sort of been evidenced by Einstein and guys like that. But basically, laws of motion, because they haven't been seen to be contradicted. So we'll just go in and have a look first. Just to say, most people know what Newton's laws say, but many people do not know what they mean, or simply not believe what they mean. So things that a lot of people think they understand but don't quite get them. So here's his three laws. Sir Isaac Newton, who was a great mathematician, wrote on a lot of different topics. His first law just says that an object at rest will stay at rest, and an object in motion will stay in motion at constant velocity unless acted upon by an unbalanced force, or by, a non-zero net force. The second law, that the force equals mass times acceleration, and third law, for every action there is an equal and opposite reaction. Seems all pretty easy, but it's when we get down to application we start to see how our understanding of it. So this first law is called the law of inertia. That's what we're just restating it there. So inertia is the tendency of an object to resist changes in its velocity, whether in motion or motionless. Okay, so these pumpkins will not move unless acted upon by an unbalanced force. Not a great example. We'll see if they come up with some better examples. Once airborne, unless acted upon by an unbalanced force, gravity and air, fluid friction, it would never stop. Okay, so its own inertia would simply means that it has this tendency, once we've caused it to move, and of course it wouldn't move on its own, it needed the golf club to a force to hit it, and once it goes into motion, it wants to stay in that motion and needs an unbalanced force to stop it, and that would be the force of friction when it hits the green here. Of course, gravity pulls the ball down so it impacts the earth, and then friction starts to apply. Okay, just saying what we said before, this golf ball would sit on the tee forever. Okay, see another example. So why then do we observe everyday objects in motion slowing down and becoming motionless seemingly without an outside force? Okay, so we see that we don't sort of see things in constant motion. And this is because it's a force we sometimes cannot see, and that's the force of friction, is the unbalanced non-zero net force that's stopping things from staying in motion. Okay, objects on Earth, unlike frictionless space, objects on Earth, unlike the frictionless space the Moon travels through, are under the influence of friction. Okay, this is the unbalanced force we're talking about. Therefore, there are four main types of friction. Sliding friction, like you see when you go ice skating. Rolling friction, like when you see bowling. Fluid friction, air or liquid, air or water resistance. Static friction, that's initial friction when moving an object. So this is static friction when you've got an object that's sitting there and it's not moving. You have to overcome friction to get it to move, and then it'll have either sliding or rolling friction you'll have to deal with. Okay, so I'll just go on to the next one. Okay, so if we just, we're going to move this down a little bit. Okay. Slide a book across the table and watch it slide to a rest. the book comes to a rest because of the presence of a force, that force being the force of friction, which brings the book to a rest position. So the fact that you push a book and it stops without there seeming to be a force to stop it, it looks at first like it's a contradiction to Newton's law of inertia. But the fact is there's this unseen force of friction which is actually opposing the motion and actually brings it to rest. So that's the point they're trying to get at here. In the absence of a force of friction, the book would continue to move with the same speed and direction forever, or at least to the end of the tabletop. So Newton's first law on you, don't let this be you, wear seatbelts. Okay, so what's obviously happening with this car? The car is travelling down here. Now the brick wall stops the car, but the body, the person, is not rigidly connected to this car. So the person has a tendency to want to keep moving forward with the same velocity of the car until a non-zero net force stops him, and that net force, non-zero net force, is going to be when he clunks into whatever's lying over here. Okay, pretty obvious that one. Okay, your second law, and that is that the force is, so if you apply a force on an object, then to an object of mass m and acceleration a, then we can calculate exactly what that force is by multiplying its mass times its acceleration. Now another way to say that is the acceleration of an object, how much you can get it to accelerate, is directly proportional to the force you apply on it, how much you pull or push it, and inversely proportional to the mass. Okay, that makes sense, doesn't it? If you want to accelerate something, it's a lot harder to accelerate big objects than it is smaller objects, and the more force you apply, the more acceleration you'll get in general. Okay, that's just stating that again in the same way. Okay, remember that mass needs to be measured in kilograms. Okay, that's the unit of mass. Mass is a measure of how much stuff or how much matter is contained in an object, and acceleration is measured in meters per second per second. We've talked about this before. Okay, the unit of force is in newtons, named after Sir Isaac Newton. So 1 Newton is equal to the force required to accelerate 1 kilogram of mass at a rate of 1 meter per second per second. So in other words, if you had a 1 kilogram block sitting here at rest and you wanted to accelerate it such that every second its speed would increase by 1 meter per second, then you would need 1 Newton to do it. So in other words, if at time equals 0 it was at rest, after 1 second this block would be moving at 1 meter per second. After another second it would be moving at 2 meters per second. After 3 seconds it would be moving at 3 meters per second. So you can see that the speed increases at the rate of 1 meter per second every second. That's what we mean by 1 meter per second per second. Okay, how much force is needed to accelerate a 1400 kilogram car? 2 meters per second per second. Okay, this is a really bad, I don't know why they put it in this color, you can probably hardly read it. So we write the formula, force equals mass times acceleration. Fill in the given numbers and units, so force equals 1400 times 2, and that gives us 2,800 newtons. Okay, there's our symbol for newtons, it's just a big capital N. Okay, simple formula. So we see here, I'll just move this out the way a little bit, put me down there for a tick. And you can see here's just a little table about mass and acceleration. So if we applied 10 newtons of force to a mass of 2 kilograms, it would accelerate 5 meters per second per second. If we double the force on the same object with the same mass, it'll accelerate at 10 meters per second per second. Okay, if we 20 newtons and we get 5 meters per second out of it. We want to know what its mass would be. Okay, and it would actually be 4 kilograms. Okay, because acceleration equals force divided by mass. So it'd be 20 divided by 4 equals 5. And this one over here, we've got some unknown force, a mass of 1 kilogram, and we want to get 10 meters per second out of it, and we're going to have to give it 10 newtons. Okay, and this one over here, we've got a missing number here, so acceleration once again is force divided by mass. That'll be 2 meters per second. So have a look at that and use it. It's all based on the use of the formula force equals mass times acceleration, and you fill out that table. We can give you a little bit of practice at working out those sorts of problems. Okay, so it's a bit more rambling. Well, Newton's second law proves that different masses accelerate to the Earth at the same rate, but with different forces. Okay, so here's the case if you've got a 10 kilogram mass, a 1 kilogram mass. You can see that the force on them, this one's been pulled down by 98 newtons, this one's been pulled by 9.8 newtons. But acceleration is force over mass, so it's 98 over 9.8, which gives an acceleration of 9.8 meters per second. This one's here, 9.8 over 1 kilogram, it's 9.8 meters per second. So they've both got exactly the same acceleration. So yeah, the bigger one's got a bigger force, but it's got a bigger mass. This one's got a smaller force, but it's got a smaller mass. And it's the ratio of force to mass which is exactly the same. Okay, so we'll just leave it there for now, and that's a fair bit to take in, and we'll come back in the second video.